Okay. All right, so this is lesson 25. And if you take a look here at what we are doing, we are going to be talking about special cases and also an introduction to limits. Limits are from calculus. So if you take a look here at number 1, graph by factoring and finding the key values listed below. So you're ultimately going to graph it the same way we've been doing, but of course this problem is in a slightly different format. You have to actually combine those two fractions, either with addition or subtraction, before you can go ahead and actually find that list and then graph it. So in order to do this, you are adding fractions. How do you add fractions? What do you need? A common denominator, and more specifically, you need the LCD, meaning the least common denominator. So in order to find the least common denominator, you actually want to start the problem by factoring all of your denominators. So starting with 2x minus 2, you're going to factor out a 2. That will give you an x minus 1. Then you're going to factor this denominator, so factors of 3 that add up to be negative 4. That would be x minus 3 and x minus 1. Again, can't stress enough how important factoring is. So when you now go to make one big fraction, okay, finding not only a common denominator, but the least common denominator, you want to look at your blue factors and you want to look at your red factors. You are hoping that there is something in common. If there is something in common, your denominator will be smaller and your life will be easier. So hopefully you can see here that there's an x minus 1 in both. If there's an x minus 1 in both, you only need one copy in your LCD. So again, if there's a common factor to both, you only need one copy in your LCD. Then you need everything else. So you also need a 2, and you also need an x minus 3. But again, the fact that you only need one copy of x minus 1 as opposed to needing 2 copies really is going to make your life a lot easier. So once you have figured out what the LCD is, and again, the LCD is that denominator, then you have to figure out what is happening on the top. So take a look at this blue, and then take a look at the new LCD. Whatever you would have to multiply the bottom by to get the LCD, you also have to multiply the top. So in this case, you would have to multiply top and bottom by x minus 3 and x minus 3. By multiplying the bottom by x minus 3, it turns it into the LCD. By multiplying the top by x minus 3, you actually have to FOIL this. So you're going to have to multiply x plus 2 times x minus 3. We'll do that in a minute, but for now, let's write it so that we know what we're doing. Then, very, very important, this is a subtraction. Any problem that is a subtraction as opposed to being an addition, you just have to take extra care to make sure that you are including it. Then, in order to take the second fraction and find the LCD, whatever you have to multiply the bottom by, you also have to multiply the top. So what would I have to multiply this bottom by in order to become the LCD? Just 2. So you're multiplying top and bottom by 2 over 2. Just to kind of make the top a little bit easier, I'm going to put the 2 in the front, and then in a parentheses, negative 2x minus 1. So take a minute to look at that, okay? Finding common denominators, certainly of fractions you guys are used to. Doing it in this case for rational expressions should have been something you've seen in the past, but perhaps not lately. So any questions on this step? How to find the LCD or how to find the numerators? Please do not try to cancel anything from this step. You cannot cancel anything from the top and bottom as long as the top is addition and subtraction and the bottom is multiplication. So now we have to actually compute this. So I'm going to leave my denominator unmultiplied, so leave it factored. And again, hopefully you have plenty of room there. Then on the top, you're going to have to go ahead and actually do the work. So you're going to have to start by doing a FOIL. So x plus 2 times x minus 3. If you FOIL that, you're going to get x squared minus 3x plus 2x minus 6. Then you have to distribute this negative 2. So if you distribute the negative 2 to the negative 2x, you're going to get a plus 4x. If you distribute the negative 2 to the negative 1, you're going to get a plus 2. Again, please do not think about trying to cancel anything from the top and bottom. You cannot do that if the top is addition and subtraction and the bottom is multiplication. Not a thing. You should now go ahead and clean up your top by combining like terms. So x squared is going to be first. If you combine all of your x's, it looks like you have negative 1x plus 4x. So that is going to give you a 3x. If you combine your constants, you're going to get negative 4. All still over your LCD. And then if you are ultimately going to graph this, just like we did yesterday, you have to factor one more time if possible. So on the top, factors of negative 4 that add up to be positive 3. What do you think? Positive 4 and negative 1 all over. I'm just going to give myself a little bit more room here. So this is going to give me x plus 4, x minus 1 all over 2 times x minus 1 times x minus 3. And then, of course, hopefully you can see that because there's a pair of x minus 1s, I can go ahead and reduce one more time to be x plus 4 over 2 times x minus 3. Well, that was certainly fun for the whole family. And again, I have designed these problems very purposefully. Like, it's possible that at some point in a problem, this will not factor, but because I have so lovingly prepared these problems, it probably will, because I want you to be able to keep going. So if you find yourself in a case where things are not factoring, probably a little bit of a problem. But okay, so we're finally down to here. So now we have our problem. And once we're down to here, honestly, it should be just as easy as it was last night. So whole, there was one. It was at 1 comma something. Remind me, how do I find the something? Plug it into the simplified form. So if I plug it into the simplified form, it's going to give me a 5 on top. It's going to give me a 2 times negative 2 on the bottom. That is going to be negative 5/4. Anybody know what's the decimal equivalent of negative 5/4? Okay. And again, I think that's something reasonable that you should know. And so you can go ahead and graph that as a literal open circle. So 1 comma negative 1.25. Okay. Okay, to find the 0, again, a 0 is a non-canceling factor of the numerator, which looks like x plus 4. So if you go ahead and set that equal to 0, you're going to get a 0 of negative 4. You go ahead and add that into your list. To find the y-intercept in this case, we never really had a nice standard form, so you have to be a little bit more cautious here. If you're going to find the y-intercept, you just want to go back to your old way of doing it, which basically means put a 0 in for all the x's. You can do it from the reduced form or from the unreduced form. It doesn't matter. Probably a little bit easier to use this one. So everywhere there's a x, put a 0. So that's going to give you 4 over 2 times negative 3, which is going to give you 4 over negative 6, which is going to give you negative 2/3. So 0, negative 2/3. And again, just to point out why we had to do that a little bit differently, at no point in our steps did we have the top and bottom both multiplied out. So we didn't really ever have a version of standard form that we could use, which means we kind of have to, work backwards and just put a 0 in for all the x's. Where is there a vertical asymptote? X minus 3, which means 3. So you can go ahead and put in your vertical asymptote here at 3. Remember, of course, one vertical asymptote means 2 pieces of the graph. Be a little bit careful here when it comes to your end behavior, okay? Remember, when you're comparing degrees, you can compare them from any form. In this case, I actually would recommend that you use this purple one. So if you think about the biggest degree on the top is just going to be a 1x. What would be the biggest degree on the bottom if you distributed? What would be your leading term? 2x. Tell me something about the degrees. They're the same. So is it horizontal or slant? It's horizontal. And how do you find it? It would be 1/2. So we haven't really had many fractional exponents, not exponents, fractional asymptotes, but no biggie. So y equals 1/2. Okay, and then finally, last piece of the puzzle, you have to actually graph it. You know there has to be two pieces. You know that the first piece has to look like this. And I know those points are pretty close together, but it is what it is. You have to approach each asymptote, go through the 0, go through the y-intercept, and go through the hole. Then there has to be a second piece. The second piece has to be to the right of the vertical asymptote. It can either be above the horizontal or below. Which one does it have to be? Has to be above, again, because there are no more x-intercepts. And again, as far as where that piece is, you can find an actual point by plugging in 4, 5, 6, or 7, or because it's just a sketch, I don't care where you draw it as long as you draw it. Remember, your end behavior should always be legit. So your graph is, in fact, approaching a half at each end. And then domain and range. So when it comes to domain, from left to right, the first place you're going to take a break is at the hole, which is 1. The second place you're going to take a break is the vertical asymptote, and then 3 to infinity. How about the range, bottom to top? What's the first y value that you have to skip? Negative 1.25, then negative 1.25 to a half, and then a half to infinity. And again, like I mentioned yesterday, I've been mixing and matching my decimals and fractions. I don't really care which version you use as long as it makes sense to you. Yes?
Can you just go over like some horizontal asymptote?
Sure. So to find the horizontal asymptote, remember you have to compare the degrees. You can compare the degrees really at any step, but in this case, it's probably easiest to look at this one. So if you're looking at this simplified version, the biggest leading term on the top is just this 1x. The biggest leading term on the bottom is when you multiply 2 times x. So then you're comparing a 1x on the top to a 2x on the bottom. Because they're both just x, they have the same degree. Whenever you have the same degree, there's a horizontal asymptote, and the way that you find it is by doing the leading coefficient on top divided by the bottom. Anybody else with a question? So that was one portion of today's lesson, making sure that you can add or subtract with a common denominator, and then really it's just more graphing practice. If you go ahead and turn to page 2, these are 2 very special cases, okay? We haven't seen any like this. I don't know how many more we would see like this year, maybe 1 or 2, but this happens a lot next year. So again, it's just a little bit of a preview. So take a look, if you would, at number 2. Notice I don't have a list for you of things, and there's a reason for that. But if you were going to try to graph this, what would be the first thing you would try to do? Factor. So how do you factor the top? Difference of squares, x plus 2, x minus 2, all over x plus 2. Tell me something about those x plus 2's. They do, in fact, cancel. And then here's why this problem is what I call a special case. After you cancel out those x plus 2's, you are left with just x minus 2. Technically, x minus 2 over 1. X minus 2 is no longer a rational function. You don't have to use those rules or find that list because you don't have any variables in your denominator. So sometimes it starts as a rational function, but it doesn't end up that way. Seems like maybe that's harder, but it's actually much easier. So this x minus 2 is no longer a rational function. It's a line with a hole in it. You still have to take that canceled factor and find the hole, but when you go to graph it, it's literally just a line. Where is that hole? So the hole is at negative 2 comma something. Why do I know negative 2? Because of the canceled factor. In order to find the y value, you would have to plug negative 2 into the reduced form. So negative 2 minus 2 is negative 4. So again, because of the fact that all you're left with is x minus 2, no variables on the bottom, this is no longer a rational function, and I don't need that list. So how am I going to graph this? Well, I'm going to start with the hole, negative 2, negative 4. Again, open circle. And then how do you graph the line x minus 2? Well, you start at the y-intercept, which is negative 2. Then you go up 1, right 1, a couple of times. Down 1, left 1. And notice that when you go down 1, left 1, you, of course, go right through the hole, which is what should happen. If you then go ahead and connect the pieces, and again, you're connecting it with a solid line, not a dotted line. It's not an asymptote. It's literally just a line with a hole in it. So again, because it's different than all the ones we've done so far, some people think that means it's hard, but I actually think it's much easier. It's just a line with a hole in it, and then domain and range like always. So domain from left to right, the only x value you have to break at is -2. And then your range, the only y value that you have to break at is -4. So if at some point in your mathematical career, whether it be tonight or on the test or not till next year, if you wind up with no variables on the bottom, it is no longer a rational function. You still have to find the holes, but you can graph just like regular. Any questions here on number 2? Okay, how about number 3? So again, there's no list. There's a reason for that. Let's go ahead and start by factoring. So if you take a look at the top, let's try to factor this first. So x to the 4th minus 5x squared plus 4. Remember, of course, that is quadratic form, not quadratic formula, but quadratic form. You are still looking for two things that multiply to be 4 and add up to be -5. But instead of x and x, you're going to do squared and squared. So what are factors of 4 that add up to be -5? -4 and -1. So that is my numerator. Hopefully you would agree that this factors more. So I'm going to keep the negative. I'm actually not going to factor the x squared minus 4, and I'll tell you why in a second. I am going to factor, however, the x squared minus 1. How do I do that? Okay. And why did I factor that? Well, hopefully you realize there is also an x squared minus 1 on the bottom, which means I can factor that bottom to be x plus 1, x minus 1 as well. So again, just to make sure this is clear, this is just the numerator. And then I factored the orange, but I didn't factor the x squared minus 4. And there's a reason for that, because I know what's going to happen. If you had factored it, you could always remultiply it if needed. Take a look at the top, take a look at the bottom. Tell me one thing that cancels. The x plus 1s. Tell me something else that cancels. So how many holes am I going to have? 2. So this problem, h of x, okay, is just going to be left with negative x squared minus 4. And again, the reason why I didn't factor that is because I'm actually now going to distribute the minus. And again, that's because I know what's happening, and I know that that's the easiest version for which I'm going to graph with. So negative x squared plus 4, this is a quadratic, no longer a rational function, with 2 holes. One of those holes is at 1 comma something. The other hole is at -1 comma something. In order to find those y values, I'm going to plug in for this x. So if I plug a 1 in, I first square it, then I make it negative, then I add 4. So that is going to give me a y value of 3. And it turns out you get the same y value if you plug in -1 for the same reason. First you would square it, then you would make it negative, and then you would add 4. So this is just a quadratic with 2 holes. I'm going to start with the holes, so 1, 3, and -1, 3. And then I know we've been focused on rational functions, but you also have to remember how to graph quadratic. So negative x squared plus 4, what's the y-intercept? 4. Is this graph going to face up or down? Down. What would be the x-intercepts? If I set it equal to 0 and I solve for x, I'm going to get x squared equals 4. So x equals plus or minus 2. And again, let's say that you didn't remember that, okay? Remember, you can always plug in x's and get back y's. But here's what this is going to look like. Again, it is no longer a rational function. It is just a quadratic with 2 holes in it. Careful with your domain and range. So when it comes to domain, I have to break at each hole. So at -1, +1, and then to infinity. And then be careful with the range. So when I'm doing the range, I'm starting with -infinity. I have to break at the y value of the hole, which is the same on both sides. Then I'm going from 3 all the way up to 4. 4 is the highest that the graph ever goes, which means you can use a bracket. So again, take a look at the first 2 pages. Page 1, making sure you can add or subtract via common denominator. Then page 2, making sure that you can understand that there are sometimes special cases. So any questions about any of that before I give you a little preview of some calculus? Okay, I'd rather you get your calculus from me than out on the streets. Important stuff here. It's true. They don't know what they're doing out there. So this is a very brief introduction to limits. You guys are going to have a whole chapter on limits at the end of the year. It's the last thing we'll end with and the first thing we'll do next year. But because of what we're doing right now with these rational functions, with these asymptotes, the left side, the right side, it does make sense to talk about it now. So probably you've heard the idea of a limit at some point. Finding a limit in calculus asks you to consider what y value is the graph approaching, even if you don't actually get there, as x is approaching some value. So this is not all that dissimilar than what you did in the homework last night. You were approaching some x from the left and from the right. We're going to continue doing that now, but we're going to call it a limit. In order to make sure that everybody is doing the same thing, we have to have some notation that differentiates between a left-sided approach and a right-sided approach. So differentiating between the two approaches, that is called a one-sided limit. Sometimes limits just want you to go from the right, sometimes they just want you to go from the left, and sometimes they want you to do both. So I could say to you the word right, or I could give you the following notation. A limit from the right, you'll see a little positive in the superscript of the limit. So that little plus sign there means you're approaching the value of c, but only from the positive side, aka the right side. If I want you to approach something from the left side, I'm going to put a little negative up in the superscript. That is how you'll know that you're approaching from the left side only. You can have a right-handed limit, you can have a left-handed limit, and then you can have what I call a full limit. A full limit means it doesn't differentiate, there's no superscript. And in order for that limit to exist, you have to compare the right side limit to the left side limit. They have to be equal. If they are equal, then that is the answer to your yellow question. If they are not equal, then the limit does not exist. So again, first look at the notation. LIM means a limit. As x goes to something, I have to tell you what the something is. I can put a little plus sign, which means from the right. I can put a little negative sign, which means from the left. The f of x just means the function. Sometimes it's just f of x, and sometimes it's actually an equation. So look, if you would here, just to kind of make it a little bit clearer what each of these values means. So this f of x, this is just the function. Again, sometimes it's just f of x, sometimes it's actually an equation. This x goes to c. This is telling you what's happening as you approach c. Along the x-axis. And finally, this actual L here, what this represents is the y value. That the graph approaches. So when you are trying to find a limit, you are trying to find a y value. Where are you looking for that y value? You are looking for that y value as you get closer and closer to whatever this x value is. Again, sometimes you're just coming from the right, sometimes you're just coming from the left, sometimes you're coming from both, and you have to compare them. Once we actually get into it 5 minutes from now, it probably will seem a little bit easier. It's a little overwhelming at first. Might be too soon, but questions so far? Okay, this is a little graphic I found on the internet, which I thought was kind of helpful. They're kind of talking about these two little bugs that are crawling, which I don't know if that helps you, the idea of getting closer and closer to something. So in this particular instance, they're talking about this vertical asymptote. We've been talking about vertical asymptotes for days now. That vertical asymptote is at -2. Okay, I asked you last night what was happening as x got closer and closer to the vertical asymptote. You had no trouble telling me the answer. Now they're just asking you to do it with a limit. So notice here, this is talking about approaching -2, but from the left side. That's what that little negative up in the superscript means. So if you're approaching the vertical asymptote from the left side, that means that you are this bug climbing down this piece. As you get closer and closer to the green vertical asymptote, the bug is going down, down, down. Where is it going? -infinity. Over here on the right, you are talking about approaching the vertical asymptote, but from the right side. So in that case, you're this bug, you're on this piece. That bug is crawling up, up, up. Where is it going? It's going to +infinity. Notice here that in order for the full limit to exist, these two things would have to be going to the same spot, which they are not. So if they are not going to the same spot, you would say that the limit does not exist, and we're going to say DNE for short. So give you a second to write that down, make sure that it makes sense. And then let's try some. So take a look here first on this left-hand side here, okay? You have 3 quadratic looking things. They are similar, but they have one small but very important difference. So look at the first set of questions, f of. If I am asking you for an f of, that's not a limit. That is just a functional value. I am saying to you, when x equals -3, is there a corresponding y value? If there is, tell me what it is. If there isn't, then it's undefined. So at -3 on the first graph, that is a point on this graph. When x equals -3, y equals what? 4. How about the one in the middle? If you go to -3, there is an open circle only. There is no corresponding y value. So because there is no y value, you would say that it's undefined. Finally, in the third one, they try to trick you a little bit. Even though there's an open circle up top, if you look below, there's a closed circle. So what is the y value of this graph when x equals -3? 1. So notice that in each of those 3 cases, they have different f ofs. That's fine. Then look at the final piece. These are limits. So the limit as x goes to -3. That means that you're approaching -3 from the left and from the right. As long as those 2 pieces are going to the same spot, whatever that y value that they're heading towards is the limit, even if you don't actually get there. So in the first one, the green pieces are both going to the same spot. What spot are they going to? They're going to a y value of 4. For the one in the middle, each side is going to the same spot. Where are they approaching? 4. Even if they don't actually get there, we don't care. A limit just means getting closer and closer and closer, even if you never actually get there. That's the same thing in the last one, getting closer and closer, getting closer and closer. The fact that we don't actually get there doesn't matter. So those are kind of the 3 most typical things you're going to see, where the f of is equal to the limit, where the f of is undefined, but the limit exists, or where the f of and the limit are both defined, but they're different. All of those are fine. Similar over here on the right. So again, take a look. Starting with f of -3. F of -3 means when x is -3, what's the corresponding y value? So how about the graph on the left? When x equals -3, what's the y value? 1, that's here. How about on the right? When x equals -3, what's the y value? That's here. When it comes to a limit, if you're approaching x equals -3, the left piece of the graph is going up, the right piece of the graph is going down. Those 2 colors are not going to the same spot. If you have 2 colors not going to the same spot, then the limit does not exist, and it's the same thing over here on the right. And again, I think I mentioned, but if any of you out there are using colors and you want to use them on test quizzes and homeworks, of course, you're welcome to do that. So the last couple examples, the one on the bottom and the one on the back, this is all about graph reading. If you see something that is an f of, that means you are looking for a corresponding y value. If you see a limit, it means you're getting closer and closer to some x, trying to tell me the y value. It could be a right limit, it could be a left limit, or it could be what I call a full limit. So take a look at A. You are approaching -2, but only from the left-hand side. So on the graph, here is where x equals -2. You don't have to draw the line in, but if you just want to visualize it, you are approaching x equals -2, but you're only approaching it from the left side. That means you're on this piece of the graph. So if you're on that yellow piece of the graph, getting closer and closer to x equals -2, what y value are you getting closer to? 1. And again, you do actually get there, but if you didn't get there, doesn't matter. For the one in the middle, you're still approaching -2, but now you're approaching it from the right side. So which piece of the graph is approaching -2 from the right side? That's this piece. As you're on the green piece, getting closer and closer to x equals -2, what y value are you getting closer to, even if you don't actually get there? -2. Finally, to answer C, you have to compare B and A. Is the green line going to the same y value as the yellow line? So then we would say that that limit does not exist. And the truth is, there isn't really a lot of work to show for these. You're literally just looking at the graph. How about D? The limit as x goes to 1. So if you're trying to find the limit as x goes to 1, that means you have to look at both sides. So here on the green piece, that's approaching 1 from the left. Here on the second green piece, that's approaching 1 from the right. Are those two green pieces going to the same y value? Yes. What is it? 1. Even though we're not actually going to get there, doesn't matter. In E, you're approaching 0. So look at the graph. At 0, you have this ordered pair, 0, -2. You're approaching it from the left side, so that's this little red piece here. Then you're approaching it from the right side, that's this little red piece here. Are those two red pieces going to the same y value? And if so, what is it? -2. Then you're approaching 3, but you're only approaching 3 from the left side. So if you're only approaching 3 from the left side, here's 3, and here's the left side approach. Bless you. As you're getting closer and closer to x equals 3 from that orange piece, what y value are you approaching? 5. Okay, now you're approaching -1. So look at the graph. Here is where -1 is. If there's no left or right side, it means you're approaching from both. So are those two orange pieces heading to the same y value? And if so, what is it? -3. Then you're approaching -3. So -3 is here. You're approaching from the left. You're approaching from the right. Are those two blue pieces going to the same y value? And if so, what is it? 0. And then for the last two, these last two are f ofs. Those are not limits. That just means when x equals this, what does y equal? So look at the graph. When x equals -2, is there a corresponding y value? What is it? 1. It's the closed circle. How about f of 1? When x equals 1, what's the y value? -2. It's the closed circle. And again, the more you do of these, the easier it will get. So to finish us up, look at the back. I have for you a somewhat crazy looking graph. Find each functional value or limit. You're going to use f of or undefined or DNE as appropriate. Just as a quick reminder, you can only say undefined when it's an f of. You can only say DNE when it's a limit. You can't use them interchangeably. Undefined means there's no y value. DNE means they're not going to the same spot. Something else to notice, there is no equation for this graph. Please don't try to make one, okay? It would be a heck of a piecewise function. It would be fun, but not needed. A few other things I want to point out here, okay? So over here on this side, there is actually a horizontal asymptote on just this piece at y equals -5. There's actually a different horizontal asymptote at this piece where y equals 2. Again, this is not actually a rational function. This is some crazy limit graph I found on the internet, so it doesn't follow the rules, but that's okay. Keep in mind here, this is what we would call that jump discontinuity. Remember, you only see them in piecewise functions, which this certainly is. Take a look here. Okay, this piece here, this is talking about going down to -infinity for the y's. So it's not a full vertical asymptote, but that piece is going to keep going down, down, down. And then there is a vertical asymptote here at -5. And again, I don't know that I'd give you one like this that has all this stuff, but I figured if you could answer these questions, you could probably answer anything. So to finish us off here with these last couple questions, f of -2. To find f of -2, that means look at the graph. When x equals -2, is there any closed circle or any defined y value? If so, what is it? 3. It's the closed circle here. How about f of 3? When x equals 3, what's the corresponding y value? -2. That's this closed circle. Nope, sorry, this one. How about f of -5? Go to x equals -5. Is there any defined y value there? So you're going to say undefined. The limit as you approach 5 from the right. So locate 5. If you're approaching it from the right, you're coming on this red piece here. What y value are you getting closer and closer to, even if you don't actually get there? 0. Still at 5, but now you're approaching it from the left side. So that means you're going to be here on this green piece. As you get closer and closer to -5 or +5 from the left side, what y value are you approaching? 0. In order to answer 6, you have to compare 4 and 5. If the left side and the right side are going to the same place, then you know that the full limit has to exist, 0. How about f of 5? When x equals 5, what's the corresponding y value? It's -3 because of the closed circle. Make sure you look everywhere. The limit as x goes to infinity. Where is x going to infinity? Over here, the very rightmost of the graph. As x is going to positive infinity, you are certainly following the horizontal asymptote off to 2. Where is x going to negative infinity? That's over here. That's a different horizontal asymptote going to -5. Someone's loving limits. That's good. How about 0? So this is the point on the graph, 0, 1. If there's no left side or right side, you have to take both and see if they're going to the same spot. So are those two pieces going to the same spot? And if so, where? 1. Now you're approaching 3, but from the right side only. So if you're approaching 3 from the right side only, here's 3. Here's the right-handed approach. What y value are you heading towards? 4. Then you're still at 3, but now you're doing the left-hand approach. What y value is that pink piece going towards? -2. And the final question for 13, look at 11 and 12. Is the blue piece going to the same spot as the pink piece? So the limit does not exist. And again, don't get confused. Undefined is for f of. The limit does not exist. So I know that that was a little bit of a longer lesson, but I promise the next one is shorter.